In 1922, Canadian Clarence Chant and astronomers from across the globe would embark on a voyage to prove a scientific theory that could alter human history. They would come from places like India, Great Britain, Canada, and the United States, and they would meet in the distant Australian outback to observe an eclipse. Chant would leave his native Toronto and would travel 32,000 miles overland by train, across the ocean by boat, and over the desert by donkey wagon. He would be joined by 7 other scientific teams at a remote spot on the west coast of Australia known as Walal, the best place on Earth to observe the eclipse and measure the deflection of light by the sun on the stars. The stakes were high, as they had just 5 minutes to get the proof they needed to verify Einstein's general relativity theory. Einstein predicted that gravity could cause light to bend. I've spent a lifetime demonstrating and communicating science to others and want to set out on a journey to understand how they got there and what we learned from that crucial 5 minutes necessary to capture what was needed in 1922. Back then, the scientific community would watch closely for the results to see how it might change our view of the cosmos. The evidence from the expedition was overwhelmingly in favor of Einstein and showed that space-time bends light. Astronomers could now begin to unlock the riddles of the universe. Today, this concept continues to be the foundation for modern astronomy, expanding the ability of big science to probe deeper than ever into distant galaxies, not only to see and understand more, but to actually listen to space itself. And it all began with Einstein, whose prediction would forever alter our concept of the universe and the idea of space-time.
People used to think that the universe was like a sort of rigid, hard, solid stage. Today we know the universe is more like a bouncy castle. When you climb into the bouncy castle, it bends, the walls bend. When you bounce, the ripples go across the castle. That's what the universe is like. Everything affects everything else. It's like a symphony. It is something wonderful that we should all enjoy because it's the reality that we live in.
Einstein predicted that gravitational waves would orchestrate the symphony of space.
What physicists like to do as a general strategy is you take something that you understand and you just give it a little flick. You give it we call it a little perturbation, and then you see what happens. And if you take space-time, if you stretch it nice and flat and you give it a little flick, you'll see that it actually has what we call a wave solution. So you'll see that ripple propagate out like ripples in a pond.
Gravity waves are incredibly significant because they're the main prediction of Einstein's theory of gravity. They're the most powerful prediction. They say that gravitational ripples come in as some messages from different parts of the universe. So it was of immense significance to try to detect these.
They're literal waves going through space?
They're waves in space-time.
Space itself, the fabric of space-time,
the very fabric
is
of
vibrating.
space-time. Yes.
It just opens this whole new direction, this whole new aspect of the universe. It's like a whole new sense that we can now observe the universe around us with.
General relativity is a physical theory about space and time. In the beginning, it was an unsolvable riddle that became known as the Einstein problem. The Einstein problem. What do you mean by that?
The Einstein problem originates in 1915 for most people. For Einstein, it goes back a little bit further. So let me tell the story a little bit. In 1905, Einstein startled the world. We call this the year of miracles. He had done this amazing work in physics. And he tells us in his writings that one day he realized that there was some connection between acceleration, that is falling, and gravity.
Through one of his many thought experiments, Einstein came up with his equivalence principle,
3, 2, 1, drop.
concluding that gravitational mass and acceleration are the same thing.
He called this the happiest thought of his life. And then he tried to work in the way that Einstein does. One of the miracles of Einstein's genius is that he first has his insights in terms of parables. There's stories that you can tell people. And so the story that he told was, if a worker fell, he would feel no weight. Then he faces the challenge of turning that story into a piece of mathematics. And so it's a long struggle of 7 years until 1915 when he learns the mathematics and is able to turn his intuition into a mathematical prediction, into a series of mathematical predictions. And one of those predictions is that gravity bends space and time in such a way that it will cause the bending of light.
And then he said, how could you measure it? Well, you needed to measure starlight being deflected past the sun, because the sun's the place where gravity is strongest in the solar system. But how could you look at starlight past the sun? The only time you could do it is in a total eclipse of the sun.
In the early 1900s, astronomers traveled thousands of miles, all to learn more about our star, the sun, especially the corona that surrounds it. When Einstein came along, he added a new dimension. He thought that you could prove his general relativity theory during a solar eclipse by using the sun's gravity to measure the deflection of light from distant stars.
When the stars are out in an eclipse and you measure the position of the stars, they're going to be different from the time when those same stars are visible at night.
Starting in 1889, the well-funded Lick Observatory had sent expeditions to observe total solar eclipses in places as far away as India and Russia. With its photographic expertise and a set of specialty instruments, Lick was the natural candidate to conduct the Einstein observation. Oh, wow! Wow, this thing is huge!
It is impressive.
What a monster!
Well, Campbell was one of the very early Lick Observatory staff. He was not one of the original staff. He came a few years after it opened. But he was among them one of the few who actually had a PhD in astronomy, who was formally educated. His specialty was spectroscopy, and it was really the tool that, along with photography, that created astrophysics.
So Campbell initially was sort of doubtful. He didn't immediately jump into the pro-Einstein wing of the scientific community, if we can describe it that way. But because he was such a meticulous scientist, his attitude was, let's go do the measurement. Independent of how difficult the measurement would be, independent of the challenges of getting it done wherever it was going to take place on Earth, he was committed to doing what science does best. And what science does best, I've told people for decades, is we try to strive for accuracy in the human understanding of nature. And Campbell's a brilliant expositor of that position.
It wasn't until 1919 that British scientist Sir Arthur Eddington would learn about Einstein's theory and make his first attempt to measure it. Tell me about Eddington.
Eddington was one of the few people who could really comprehend Einstein's new theory. As it happened, he had been sufficiently well educated in Cambridge that he was familiar with the kind of curved space-time geometry that lay at the heart of Einstein's theory.
They got there and the eclipse happened. How did it turn out for them? Did they get what they were after?
Eddington was foiled by bad weather, but the clouds did thin just towards the end of the eclipse for him, and he did manage to get a couple of photographs with a few bright stars on the plates. And this was enough for him to do some data analysis, which was broadly in agreement with Einstein's theory.
But with a little bit of averaging and things, Eddington was able to say, I've confirmed Einstein's theory, sent telegrams around the world, and instantly Einstein was famous, and the story came out. Lights were askew in the heavens. That was the headline of the New York Times. Mainly, it was Einstein was right.
Later on, there were many historians and astronomers and physicists who expressed some skepticism about Eddington's results.
The shift could be due to something else. So can you actually prove really correct that this is indeed that? Because it's actually a groundbreaking discovery supporting a theory which nobody wanted to believe.
You know, the world was agog about this, but if you had asked the scientists, they would have said, maybe. And so Wallace Campbell was one of the people who said, I'm going to nail this.
Lick Observatory at that time, they would have done at least 14 eclipses beginning in 1889. They were really known as the world leaders in eclipse expeditions and eclipse photography. And Campbell had a reputation for his precision, care, and his meticulous observing style, and all of this experience at eclipse expeditions. So to ally yourself to Campbell not only was prestigious, but it also really helped to guarantee success. Chant was eager also to participate and do something with the Einstein problem.
Director W. Campbell of the Lick Observatory, an experienced and competent observer of eclipses, decided to send an expedition to observe the eclipse for the express purpose of obtaining evidence on Einstein's theory. I asked him if I might prepare apparatus and accompany him, and he was cordially agreeable. This led to one of the greatest experiences of my life.
Well, in terms of astronomy, he was it. But there was virtually no astronomy within the university before he came along. And then he was the force behind the Dunlap Observatory, which not only has a strong research record, but also is well known to the public.
Under construction for 3 years, the Dunlap Memorial Observatory at Richmond Hill is nearing completion. The steel dome, 61 feet in diameter, will house the giant telescope, second in size only to the one on Mount Wilson, California. Canada's new telescope will have about 100,000 eye power and will make the moon appear to be only about 50 miles distant.
The reason for having such a great telescope as this is because the greater the area of the mirror, the farther into space one can peer.
So see, he and this little party, including his family, went off to the depths of Australia to observe this event.
Alexander Ross from UWA advocated that Walal was the best location because the eclipse path was a long path. It started almost at Ethiopia and went all the way across the Indian Ocean, then came across Australia. But the British immediately responded very negatively, and they said that Walal was an awful location at the edge of the desert, and there were no roads and completely impossible to go there.
The weather report the last 25 Septembers showed that it had rained there only twice in that time, a small fraction of an inch altogether. The problem was how to get there. Elizabeth Campbell.
If William Wallace Campbell was my Zeus in the story, Elizabeth is Hera. She was just an incredible companion. She was involved in his expeditions around the world. She was the social manager of the group. She was also someone who was committed to the science.
In addition to her planning contributions, she also operated instruments on the site. So she was in every way an important and contributing member of the expeditions.
Campbell finally decided on Walal because the Australian Navy offered a schooner to take all the eclipse observers from Fremantle straight to the beach. There were 7 expeditions. India sent one. Freundlich sent an expedition from Germany. Chant sent one from Canada. Campbell sent one from the US. The Brits sent one, and 2 Australians.
To get my apparatus constructed and tested was occupying all my spare time. I was taking my wife and daughter, and I was joined at Victoria, BC by R.K. Young of the Dominion Astrophysical Observatory there.
Now, I understand that he was really good at building instruments.
Yes, he was, which is, of course, why Chant wanted him, because he realized you're on the western edge of Australia, middle of nowhere in those days. He wanted someone that knew what they were doing.
So what did he do? What was his role?
Well, Young, he put the equipment together, built what was needed, aligned the optics. You know, he handled all those meticulous little details that you need to be successful.
Wow. So what is this place?
So this is one of the main stock areas for the U of T archives.
Okay. And this is where you have Chant's actual slides.
That's where we have them. In fact, they're right behind you here, so I'm just gonna grab them. Okay, do you want to see some of these?
Should I turn this on?
Yeah. There we go.
Color map of Australia.
On Friday morning, the Lick Observatory party arrived. Young and I were there, and I was the first to shake Campbell's hand. The dock was crowded with people to see us depart. Our expedition had aroused much interest, and indeed, there were a number of other passengers who aroused our curiosity. One of the citizens asked us if we were going to Walal. He said it was a little hell.
So that must be the larger group.
Yeah.
Yeah.
Both the Americans and the Canadians?
Mm-hmm. So I know for certain that that is Campbell, and that's his wife.
Right in the center.
Yeah. There's Chant and his wife right beside them.
Right.
R.K. Young must be at the end there.
Okay.
Oh, it's a cool schooner shot. Look at that.
Ooh, that's the schooner that took them up the coast of Australia.
On the schooner, there were 36 persons. The cargo was about 67 tons by volume, 35 to 40 by weight.
On August 30th, Campbell and his team, which now numbered 35 and included sailors and indigenous workers, lowered the delicate equipment from the schooner down into a gasoline launch. Oh, that's the team bringing them in from the boat to the beach.
Look at this one.
Wow. Riding the surf.
One of the reasons that the British said the place was impossible was because the tides there are about 9 meters, 20 feet.
There was quite a long carry to the land, and the tide was rising and continued to do so until 4:30 p.m. By loading the cargo on the whale boat and using the motorboat for towing it, more rapid progress was made. We were met by a number of men and women. Aborigines who came in the water and carried off the parcels. One Jinn took my suitcase, carrying it half the time on her head and the rest at her side with her arm around it. And it was uncomfortably heavy, too.
The women talking sound like insects in the sun. Not a buzzing, but a high-pitched, rattly, almost metallic sound. It seems to me as if all they said was, "Bula, bula, bula."
As with all Lick expeditions, the local inhabitants were called upon for a variety of jobs, usually the hard labor. In Australia, that fell to the indigenous Aboriginal peoples. They were indispensable.
Got ashore at 9:30, low tide, waiting the last bit. Dust, flies, chaos. Began unpacking. Dinner in the open at a long table after dark. Everybody dirty and tired.
Okay, let's see what this is. Oh, I know what this is. Einstein Cafe.
That's where they did their meals and things.
Yeah.
The ground was very dry and covered with light sand. When one walked over it, with every step a cloud of fine particles rose. At once, we started to clear the land and to mark out the place for our instruments.
Now, the difference between Chant and Campbell's equipment was Chant had an 11-foot focal length, and Campbell had a 15-foot focal length.
We spent several days erecting the Einstein apparatus. First, we trued up the bearings on the polar axis, and with the help of the Navy men, we set it in place. Next, we unpacked the heavy camera, put it together, and then, with the help of our friends, put it on the polar axis. Then we covered it with black cloth and balanced it. This gave considerable trouble, and it all took much time.
Whoa! I can see we didn't talk about where we were going to put it.
I'm just imagining those people carting this stuff from the ship across a beach. Wow.
Here we go. This is the one of the two identical lenses for the 15-foot.
Wow. Wow.
So it's a single, very large quadruplet lens with a 15-foot focal length, and its intention is to make a field of view around the sun on the photographic plate really flat, with as little distortion as possible.
Oh, okay.
And there she is.
Everything's so heavy and well made. I mean, it's amazing.
Yeah.
Wow.
Chance lens, I think, is a little smaller. It's an 11-foot focal length, whereas this is a 15-foot focal length.
Wow, this is really heavy.
It is really heavy.
All right.
So here it is.
Wow. Ooh, I can't believe how heavy these things are.
It is very heavy.
There's the lens on one end, and then there's another lens on this end.
The same thing on here. The only markings on it is this little word here that says front.
And then this whole thing goes on a big frame.
The whole thing goes in a big frame, and that frame in turn goes in a very geometrically precise mounting that allows it to follow the stars, or rather to counteract the motion of the Earth, so your photograph doesn't get blurred.
And at the other end of the tube, they put photographic plates, which were big square pieces of glass that were covered in gelatine emulsion for the photographic process.
So that is
That is it.
Young and Chant.
And he's got the photographic plate there at the bottom.
Yeah, see the size of them?
Yeah.
They're massive.
Wow.
Our next job was to erect our observatory for the Einstein camera. This was a protection from the wind and the hot sun. But within our circular observatory, the dust underfoot was very bad. So we got 2 men to carry coarse red sand and spread it on the floor. This was an improvement.
Campbell actually internalized this challenge of the Einstein measurement. He did not want to repeat the mistakes that he had made in Kiev and Goldendale. And from our research, it appears he literally lost sleep worrying about what was the outcome, what would the outcome be, and B, whether he would be able to meet the challenge of making the measurement.
At 12:03 was the first contact. In a few seconds, one could see the little piece bitten out of the lower left portions of the sun by the moon. The little piece grew larger. Keene, standing on a wooden box, began counting in a loud voice. 10 minutes to go.
So these clocks here actually provided the time for the Walal expedition. Whenever you're taking recordings in astronomy, it's really important to know exactly what time it is. It's very important to have that everyone's doing stuff at the same time. And so Perth Observatory's main role was actually providing the time for the team. So they've got here the telegraph station right here, and then you've also got the telegraph line as well. They were taking the time wirelessly from Perth and also Adelaide Observatory, plus Bordeaux in France and Annapolis in America, and making sure that time was correct. And this was so that they knew when they could start getting their shots.
6 minutes, 2 minutes, 30 seconds. And when Dr. Campbell actually saw the sun disappear behind the moon, he shouted, "Go!"
The eclipse lasted 5 minutes and 11 seconds.
And the totality is very important, how long you will get the totality. So 1922 expedition is extremely important because the totality they had for 5 minutes. That's extremely rare. Long totality time.
Keene, having the chronometer before him, started counting seconds. 1, 2, 3, and kept it up until the entire total phase was over.
Campbell did these 2-minute exposures to really try to burn in more stars, whereas Chant did 45-second exposures so that he can get more shots.
We had some trouble with our exposures. A too violent pull was given to the cord, and it broke. We were horrified. Were we going to lose all our efforts? Hastily deciding on exposures, we secured 1 plate at 9 seconds and 2 at 45, which gave good negatives for our purpose.
At Walal, the Americans led by Campbell, the Canadians led by Chant, would all get the evidence they needed to solve the Einstein problem. But other international expeditions weren't so lucky.
There were other expeditions on the other parts of the paths of the eclipse across Australia, and none of those expeditions succeeded. There was an Indian expedition at Walal. Their equipment completely failed. So these things are difficult.
So it's exactly what it says it is. Yeah.
That's the actual eclipse.
At 45 seconds exposure.
Wow, yeah. The corona is so beautiful. It's just the way it doesn't have an outer edge, it just kind of fades out. It's very beautiful.
This is one of the plates that proved the general theory of relativity.
Oh, yeah.
You can see of course it's a negative.
Yeah, but that's the sun, that's the eclipse.
That's the sun, right. And the circles that you see have been drawn on later and are to indicate the positions of the stars that were measured.
Wow. And they took that all the way to Australia and back.
Yeah.
Wow.
So there it is.
Thank you.
Proof of general relativity.
This was an enormous improvement over the Eddington results because there was a lot of ambiguity left from those. None of that ambiguity was present after Campbell and his expedition came back with their observations.
It wasn't until the end of the 1920s, actually, that people started, in the scientific community, saying Einstein's right. So people really wanted it tested again, and again, and again.
The theory would continue to be tested long after the late 20s. Decades later, radio telescopes were picking up clearer signals from celestial objects that were further away. And by the early 1960s, astrophysicists like Erwin Shapiro had come up with a new way to test general relativity using radar. Now, when you did the experiment and Mercury was on the far side of the sun, so your echo was going to come close to the sun on the way back, did you see the bending? Or
Not with the radar. We had no sensitivity to the angle that was relevant, but we did have sensitivity to the time delay, which was my contribution.
So what causes the time delay?
The fact that the signal is going close to the sun. It's not that the path is longer because it's bent. That's not the case. The signal actually goes slower according to general relativity as it passes the sun. And it's this difference in echo time that is the so-called Shapiro delay.
So the timing delay is because the gravitational field of the sun slows down the signal.
Yes.
Einstein's theory continues to pass even more rigorous tests, remaining our best explanation of the phenomenon of gravity. Remarkably, it predicted things like gravitational waves, ripples in space-time caused by some of the most violent and energetic processes in the universe. These ripples travel at the speed of light, carrying information about their origins as well as clues to the nature of gravity itself.
So Joe Weber was really the first physicist to recognize that you could measure a gravitational wave in principle, and he came up with a bar. So this is a detector that really is intended to ring at a specific bell frequency. It has a sort of bell resonance up around 1 kilohertz, 1,000 cycles per second. Yeah, you can hear it.
Okay.
You just lean in.
Boy, that's pretty high.
That's really high. So
I'm just barely hearing it. Yeah.
Yeah, I mean, and of course, if a gravitational wave causes that bar to ring, it's not going to ring very loudly at all.
So the gravitational wave is causing the bar to grow and shrink.
It's really causing the space to grow and shrink, and the bar goes along for the ride.
Imagine that you can build something like a radio receiver, but instead of receiving radio waves, you can sense fluctuations in space-time itself. So if you think of the universe as a cosmic symphony that's emitting this music, this signal, then physicists over the last 100 years have been trying to find a machine that can turn that signal into something that we can hear, into something we can observe.
When I came back to Australia, I decided to build a detector here. Now, we wanted to build the very best in the world, and instead of using bars of aluminium, we decided to use bars of the metal niobium. So we called our detector Niobe, the goddess who niobium is named after.
This bar of niobium will be used to record the gravity waves or vibrations.
And if I tap it, it'll ring, as you can hear, and ringing of this sort will be induced by a passing gravity wave. So if we discover gravitational radiation, it will confirm Einstein's theory of gravitation.
After more than 10 years of construction, changing, improving, modifying, we reached a fantastic sensitivity, and it rang for about 1 month after you pinged it like this. What we were interested in was whether there was a change in that ringing when a gravitational wave hit it. 5 bars like this operated around the world for 7 years listening continuously. We were hoping that all of these detectors simultaneously would go off, or nearly simultaneously. We searched and we searched and we listened and we listened, and the universe was silent. We just weren't sensitive enough. It needed the next step, which was laser detectors, to reach the sensitivity to be able to hear gravitational waves.
With the use of mirrors, laser interferometry merges two laser light beams to create an interference pattern, which measures things like the merging of black holes or collisions of neutron stars.
After the prototype design of LIGO in the 70s, from the early 90s when it was approved to when it finished construction in the late 90s, there were 15 years, more than 15 years, where we did take a lot of data and did a lot of upgrades and tuned that radio more and more. That static and crackle is changing, it's getting better, we're getting closer, but you couldn't hear the music yet.
The stretching of space made by anything is actually really, really small. The stretching of space made by the Earth is about 1 part per billion. The Sun makes it to 1 part in a million. The stretchings are so small that we have to make the most sensitive measuring devices that have ever been made. You can determine exactly what is out there from what you hear. Most of what we hear are sounds a bit like this. Whoop. And these little whoops are the sounds of black holes spiraling together and getting closer and closer and closer, and finally ringing a bit like a bell is ringing. So it's the whoop, and then a little bit of a ringing note at the end. And all that completely describes the system. So we can tell exactly what it is, also how far away it is.
So there are probably many different kinds of gravitational waves out there. I mean, everything that has mass and that is kind of moving, then it's emitting gravitational waves. But the loudest ones that we've been able to detect so far are from these pairs of black holes or neutron stars that are spinning around each other. And as they're doing that, they're getting faster and faster and closer together until they merge. And the gravitational wave kind of follows the similar frequency evolution of these two objects going faster and faster. So it sounds like a chirp. So it starts off at lower frequencies and it goes whoop. And that's when the merger happens and it goes quiet.
So these are galaxies coming together, and their black holes in their centers come together, orbit around.
That's right.
And that's what shakes space.
So if that's where this signal is coming from, then we're seeing evidence of galaxy collisions and black hole collisions from all over the universe. And these waves have vibrated the fabric of space-time, and those waves have just been traveling towards us from all over the universe.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Nature just handed us a signal. This great big blazing beautiful signal.
the time of the first detection, I had just started graduate school in 2015. So I came into graduate school thinking I would work with light like most astronomers do. And then there was this new discovery, and that I think changed things for the whole field of astronomy. And for me personally, it gave me this new research direction. The fact that you can have two massive objects causing space itself to ripple and to create these waves that radiate away and carry that information. Theoretically, people were arguing about that back and forth for a long, long time. And then there's the technical challenge of actually detecting these really tiny ripples.
So we've got these two long arms at 90 degrees to each other like an L, with mirrors on either end. Just fundamentally, how does the laser interferometer work? How does it detect gravitational waves?
There's kind of two things you have to do to make a laser interferometer. You have to make mirrors really still, and laser light very pure.
Okay.
You take that laser light and you inject it onto a beam splitter. The beam splitter is a 50-50 mirror. It transmits half the light in one arm and reflects half the light down the other. The light marches down, hits and mirrors, reflects back, and then combines back at the beam splitter, and the combination of the light comes out through the output port.
Okay, now what happens when a gravitational wave passes through?
A gravitational wave squeezes on one axis and expands on the other. It's not that the arms are moving around in a sense, it's the space between the beam splitter and the end mirrors that's getting expanded on one arm and contracted on the other, and then vice versa.
Oh, wow. This is the actual tube.
This is not the beam tube itself, but the component that takes the input light from the main laser to the beam splitter.
Okay, so this is where the laser beam starts.
Laser beam starts here, injects down here, hits the beam splitter, reflects up one arm, transmits through the other.
Okay, got it.
This is the last chamber in the output port, the so-called ham-6 chamber. That's where the photodiodes that see the light from the two arms reside. So that's really the business board of the gravitational wave interferometer. It tells you whether the arm lengths are changing for any reason at all. That could be gravitational wave sources, or it could be trucks driving by on the 240 highway. So we originally ran an initial LIGO from 2000 to 2010, two interferometers here in the same vacuum envelope. But when we got to building advanced LIGO from 2010 to 2014 for the first observation run in 2015, we realized that it would be better to have those parts in another location, a new interferometer site.
Now this is going to be third LIGO on Indian soil. So it's pretty much the replica of one of the US detectors with 4-kilometer arm length. We'll be able to localize the source very accurately. Okay, so because LIGO India and then the US site, basically we are diametrically opposite. And as a result, it provides a long baseline. And if you have a long baseline, you can localize the source very accurately. But you'll also see more sources because now you have one more detector with similar sensitivity, and as a result you will see much deeper in the sky.
One of the biggest technological challenges now, so we have sufficient power circulating in the arms to push down that hiss and crackle at higher frequencies, and we have a fairly good understanding of how to stabilize the mirrors so they're not moving around relative to each other. And now we're stuck with what's called thermal noise. So this is actually the atomic motion on the surface of the coatings that are reflecting the light back and forth inside the arms. So we have to improve material science. All right, we're actually headed up to the third floor.
Okay.
We're in here.
How do you get something to be very, very still at an atomic level?
But you're looking for a material that doesn't have many avenues through which energy can be lost. Because if it's got mechanisms inside it where energy can be lost, then that energy leaks out into the rest of the material and makes the atoms wobble around. So having something where we can have 100 devices on one chip, we could test, say, 100 different materials on one chip, that should rapidly speed up the testing, and then finding a good material is going to happen much, much quicker.
So how much of a difference will this make for LIGO?
It should make a huge difference.
I can say just one thing that makes me excited as a cosmologist. When we look back to the very early universe, we can't see back earlier than 400,000 years just with light. But with gravitational waves, in principle, you could see back to the very earliest moments of the universe's history, to much less than a second before the Big Bang. And that's just something that you qualitatively cannot do with any other observable that we currently know about.
So you can see the Big Bang itself?
Yeah, in principle. Signals from the end of the Big Bang or signals from an abrupt phase transition very early in the universe's history. So there's been a lot of work done about the possible gravitational wave signals from those violent phases very, very early in the universe's history. And they could show up in observations like this one.
The bending of light is still the basic principle that astronomers use to understand how objects behave as they move through space, such as activity around a black hole. So are we seeing the bending of light around the black hole when we see that image?
Light bending is the entirety of what makes our experiment possible and interesting. The light is strongly lensed around the black hole. It can actually make full orbits around the black hole. And when we see the dark depression in the middle, that's our line of sight falling into the black hole. So we're sort of looking in the black hole, not necessarily at the black hole. The ring of emission that we see, you'd actually see a ring from any angle. If we could look from the other side, we would also see a ring. And that's due to the strong lensing that the black hole imparts on the radiation around it.
What we've done recently is make a map of the clumpiness of the universe on really large scales. And the way that we did that was by using the bending of light. So we're using light from the very early universe. It's called the cosmic microwave background. This is the afterglow of the Big Bang, so it's from 14 billion years ago. And that light has been traveling through empty space for 14 billion years until it hits our telescope. But along the way, the path of the light has been bent very slightly by the large-scale structure of the universe. So the universe isn't completely smooth. It's kind of clumps on kind of millions of light years scales. And those clumps cause the light to bend very slightly. And we've been able to measure that and map out how clumpy the universe is.
So how would you compare or put into context the map that you made of the overall universe bending light and Campbell and Chant's expedition to see an eclipse of the sun to see how the sun bends light?
So they were using the mass of our sun to observe how light bends on the scale of a solar system. We're using exactly the same principle, but on scales the size of the whole universe, millions of light years. And the light has been traveling for about 45 billion light years. But it's exactly the same physics. And it's a really incredible testament to the power of the theory that what works with our sun works with structures that are millions of light years across.
So if we didn't understand general relativity, I don't think we would have an explanation for what could be the object that drives some of the most energetic events that telescopes observe. So at the center of galaxies, you can find these monsters that'll be sucking in lots and lots of gas and dust and emitting unimaginable amounts of energies that can propagate really vast distances. I think we'd be quite perplexed.
We see the effects of gravity on light every day when we look at distant stars and galaxies. You can see these amazing gravitational lensing images of the distant universe where you see the same galaxy appearing in multiple places on the sky, and it's clearly the same galaxy. It has all the same features. And the reason for that is because you're seeing light rays that have taken different paths to us from that galaxy because they don't travel in a straight line. They've been bent by the intervening stars and galaxies and dark matter. If we didn't have a theory in which light interacted with gravity, you would look at this and be, what is this? Are there like clone galaxies scattered all over the sky? Like what's going on here?
Or like when Galileo first pointed a telescope out there at the sky. We're really just at the beginning. It's not just a description of the universe, it's actually a description that we can use to discover objects in the universe that we wouldn't have known existed.
Elizabeth organized many of the Lick Observatory eclipse expeditions led by her husband William. Eventually, she would receive the deserved recognition for being a talented astronomer in her own right. Chant would get the evidence, but not the credit for proving Einstein's theory. He's known as the founder of Canadian astronomy and was an enthusiastic popularizer of stargazing. Going back to Chant and the expedition in 1922, they were trying to prove Einstein right. That Einstein, comes up with this idea, and then all the way along, people say, hey, he was right, and you wouldn't be here if he wasn't right.
Absolutely. It's a whole lineage of experimental physics to show that this theory, which was born of Einstein thinking of the simplest kind of thought experiments, bore this exotic mathematical theory of curved spacetime. And to have it be right time after time again, that's amazing. It's staggering, really.
Campbell openly believed that Einstein was wrong. When asked what his hopes had been for his test of general relativity, he said, but when his own experiment proved Einstein right, he admitted his error and never opposed relativity again.
And Einstein actually made a beautiful statement. He said, most theories suffer the fate of being found incorrect shortly after they're proposed. But for those for which this does not occur, nature only says maybe. And so he knew at that point that nature was saying maybe Albert Einstein got it right.
It's a very eloquent way of saying, I told you so.
I told you so.
Nobody's been able to prove him wrong, and yet he thought about these ideas in 1907, 1909.
My impression of him is total awe. He was a brain that's one for 1,000 years or so. He did so many brilliant things in physics. Relativity is just one of them. He really was an amazing genius.